Hi, and thanks for watching my recording. My name is Jackie Kendrick, and today I'm going to present to you a study in which we assess the potential for earthquake-triggered lava dome instability at Mount Unzen, Japan. Firstly, I'd like to thank the conveners for inviting me to speak in this session. This work was conducted at the University of Liverpool in the UK in collaboration with the University of Canterbury in New Zealand and the National Research Institute for Earth Science and Disaster Resilience in Japan. We would like to acknowledge funding from both the Daiwa Anglo-Japanese Foundation and the Marsden Fund in New Zealand. Many of you may remember the infamous eruption of Mount Unzen, which began with a phreatic explosion on November 17, 1990, following more than 20 years of intermittent seismic unrest. After a lull in activity, the eruption began in earnest a few months later, with explosions in February and April of 1991, before the beginning of a phase of continuous activity in May that year. From the 20th of May 1991, a lava dome began to grow at the summit of Mount Unzen in an eruption which captured the world's attention. The viscous dacitic lava which erupted constructed a series of 13 lava lobes which frequently collapsed, generating searing pyroclastic flows which travelled down the flanks of the edifice at up to 100 km per hour, predominantly directed down riverbeds towards the nearby towns to the east. Also to the east of the edifice sits a large ridge, the remains and powerful reminder of the devastating 1792 eruption which took the lives of an estimated 15,000 people when the Mayuyama dome unexpectedly collapsed. Although the 1990-95 eruption's consequences were less devastating, it still caused the tragic loss of 43 lives in an eruption which has helped shape the face of modern volcanology. So, why am I talking to you about this volcano today, more than 25 years after the end of the eruption? The answer is that this volcano is now topped by a loose, rubbly pile of cooling, altered, and unstable lava in a region, the Shimabara Peninsula, which suffers both monsoonal rains and thousands of seismic events per year, which mean that much of the flanks of the volcano remain in an exclusion zone due to the risk of the lava dome collapsing. The constant transport of erupted material down the riverbeds also require a constant infrastructure of clearing and reshaping, as can be seen in the aerial photograph on the right here, to keep the channels clear in case such a collapse event may occur. Nowadays, the Heisei lava dome is approximately 1,200 meters by 800 meters across, with an estimated maximum thickness of around 240 meters. At the center of the dome sit some relatively coherent lava spine segments surrounded by ongoing fumarole activity, but the majority of the dome comprises centimeter to tens of meter scale blocks, loosely balanced and pierced by joints and fractures, which during the 8 years over which I have visited the dome have shown increasing signs of breakdown thanks to progressive alteration and a harsh climate. Frequent rockfalls traverse the sides of the volcano, as seen by the channels in the photograph at the center here. The exceptional detail with which this volcano is still monitored by the Japanese authorities have revealed a long-term trend of motion of a portion of the lava dome. The LiDAR image here from Hirakawa and co-authors demonstrates the motion recorded over a 9-year period from October 2005 to November 2014, over which they found an average rate of motion of parts of the dome at 2.45 to 5.77 centimeters per year towards the southeast to east-southeast. On the right, lava lobes 6 to 9, as well as lobes 11A and 11B, are delineated, which are the areas most susceptible to motion as they overhang the steep mountainside. Considering this observed creeping motion and its precarity, we wanted to understand the lava dome's potential for seismically induced collapse. To gain this insight, we had to understand the spectrum of material characteristics of the dacitic lava dome. In this photograph, you can see that even in one of the most intact parts of the lava dome, the central spine, which marked the end of the eruption, there is a high degree of variability in the lavas. For this study, we chose to collect samples from the pyroclastic deposits in the riverbeds to the north and southeast of the volcano in order that we could select a range of representative materials without any impact on the lava dome. We selected a number of blocks from which we cored our samples for physical and mechanical characterization. We measured a range of porosity of 9 to 43% and a range of permeability spanning almost 6 orders of magnitude. From the collected samples, we selected 5 sample groups indicated in this image for the remainder of the study. These represented a low, medium, and high porosity sample, as well as an anisotropic banded sample cored in two orientations to the fabric, as such heterogeneity is commonplace in the Unzen lavas. Here you can see both cores and disks for compressive tests and Brazilian disk tensile tests respectively. Compressive strength for the materials, plotted here as a function of porosity, was found to span 17 to 45 megapascals, whilst the Brazilian tensile strength was found to be just 1.8 to 3.4 megapascals. The compressive strength was between 7 and 17 times higher than the tensile strength, depending on the sample group, with the anisotropic samples cored in opposite directions forming both end members. We also performed the same tests on saturated samples to see whether saturation itself, caused by rain at the volcano, could weaken the materials, but we found that the results were largely indistinguishable from the dry tests as shown by the plot on the right. We did, however, find that Young's modulus was slightly reduced by sample saturation, although this did not particularly extend the span of values, which was already from 4 to 22 gigapascals. Here, I also want to draw attention to a previous study of ours in which we performed a series of compressive strength tests at a range of different strain rates and showed that the Unzen lavas are rate strengthening, or, in other words, that they're susceptible to time-dependent deformation, becoming weaker at longer stressing durations, as is typical of geomaterials. So this is also an important consideration when thinking about lava dome stability. During our tests, as well as monitoring the stress-strain curves as shown in the examples here on the left-hand side, we also used acoustic emission sensors to perform active surveys of our samples during testing. In this method, we use one sensor to send a pulse and the other to receive it, and we can use Coda wave interferometry to quantify the damage induced throughout the test as a result of stressing. We can use this as a proxy for the reduction in the ultrasonic wave velocity shown here on the right-hand side, which tells us when permanent inelastic strain sets in during deformation. In our tests, we found that this onset occurred at between 60 to 80% of the time or strain to failure. Such approaches have been used at large scale during volcanic eruptions to quantify damage caused during magma propagation, including during the spine extrusion at Mount Unzen in a study by Lam et al. Which we published in 2015. We see comparable reductions in velocity of up to around 0.4%, as are seen at larger scale, and this tells us that the material is dilating due to fracture damage before the final failure event. As well as constant rate tests where you monitor the loading rate, you can also do mechanical tests under constant load, in which you monitor the resulting deformation rate. These load-hold or creep tests provide a valuable understanding of the response of materials under non-critical loads. In this study, we performed a series of stepped constant load tests based on the pre-measured strength, choosing 6-hour-long load-hold periods at steps of 40, 50, 60, and 70% of the material strength, both in compression and tension. In the example shown here, you can see how the strain, in blue, is relatively constant at each step until the load-hold step at 70% of the strength when the sample begins to creep. The plots on the right summarize this data for the whole series of tests in terms of both strain, strain rate within each load-hold portion, and for all the tests at different samples in compression and tension. Although the strain increases from one step to the next in all cases, you can see that the strain rate only increases for a few tests at the 70% load-hold portion, meaning that at values below that, no permanent damage should be imparted on the samples. This is important for the next suite of tests. In the final suite of tests, which were the ultimate goal of this study, we performed hybrid load-hold oscillation tests. In these tests, we brought the samples to a holding load of 60% of their pre-measured strength and allowed them 30 minutes to stabilize, and then applied a series of 20 load oscillations at a spacing of 2 minutes. These oscillations were intended to mimic the passage of an earthquake through a material, and indeed we used real earthquake waveforms monitored at Mount Unzen for this purpose. We scaled the events to the material strength, oscillating by plus and minus 10% of the material strength, whilst monitoring the strain response. If the materials survived these oscillations, we then returned to another 30-minute load-hold phase to observe whether the material behaved differently, and the difference in the absolute strain between the first and the second load-hold we interpret to be permanent strain resulting from the oscillations. In the case of sample failure, the degrading impact of the oscillations was clear already. Here you can see two examples. On the left, a sample in compression annotated for the different stages of the test. On the right, a sample in tension which failed on the 10th oscillation cycle. In both cases, when the oscillations begin, the strain in the sample increases from the load-hold condition, but in the surviving example, the increase in strain with each subsequent event reduces, whereas in the case where failure occurs, each event causes more and more strain. This observation, whilst fairly intuitive, is an important demonstration and one which has implications for the monitoring of unstable masses in seismically active areas. If a motion appears to accelerate with successive events, then it may be an indication of more likely imminent failure. In terms of the strain induced in the different materials by the oscillations, we posited that this may be porosity dependent. Here, we compare the increase in absolute strain between the initial and final load-hold portions before and after the simulated earthquake oscillations. In the case of compression, we can see that the more porous samples clearly suffer less permanent strain, suggesting that they may buffer the earthquakes more effectively. In tension, however, we do not observe a correlation. This is not particularly surprising considering the different failure modes of materials in compression and tension, and you can picture how a more porous rock may be more springy, if you like, in compression. Most recently, we wanted to compare what we learnt back to the volcano and decided to focus in on the impact of the Kumamoto earthquake, a magnitude 6.2 event that occurred just 40 kilometers east of Unzen on the 16th of April 2016. We used Sentinel-1 imagery to look at SAR displacements between October 16, 2015 and December 27, 2016, which spans the Kumamoto earthquake. Whilst the absolute motions are quite complicated, we can clearly see in the image on the right that portions of the dome show relative motions before and after the event, which could indicate some rockfalls or partial collapses of the dome. However, considering our experimental results, which suggested the most robust indicator of permanent damage being imparted may be an observed change in the longer-term creep behavior, and considering we already know that lobe 11 is creeping east-southeast by a few centimeters per year thanks to the work of Hirakawa et al., we decided to examine this further. In this plot, we see a preliminary look at the movement of lobe 11 throughout late 2015 and 2016. This plot indicates an increase in displacement rate after the Kumamoto earthquake in April of 2016. The average displacement rate for the points highlighted in the map to the left increased from 0.036 mm per day prior to the earthquake to 0.073 mm per day after the earthquake. This near doubling of the rate of creep of lobe 11 presents a fairly strong indication that the summit lava dome was weakened by the occurrence of the Kumamoto earthquake and that it is thus susceptible to earthquake-triggered weakening. That said, we do need to check the displacement rates against other years to be assured that these are not caused by seasonality. To conclude, in this study we used a series of load-to-failure, load-hold and load oscillation experiments on dacitic rocks from Mount Unzen to understand materials' response to different stressing scenarios in the context of long-term lava dome stability and the susceptibility to forcing by seismic activity. We observed that both the type of stressing event and the physical properties of the material control the resulting degree of damage. Standard strain-to-failure tests show that strength decreases with increasing porosity and that compressive strength is 7 to 17 times higher than tensile strength. Prior to failure, samples exhibit accelerating rates of deformation and their ultrasonic wave velocity reduces, suggesting the onset of permanent damage. Damage induced by experimental earthquake loading caused samples to suffer permanent strain and to be closer to expected failure strain after the oscillations. Under compressive stress, we see that porous samples may buffer load oscillations more effectively, although their lower absolute strength implies that a similar scale of event may render them more likely to fail. The most susceptible materials to failure were anisotropic banded fabrics, which comprise heterogeneous dense and porous layers, and although the scaling of such an observation is yet to be fully addressed, this suggests that heterogeneous masses, such as the Mount Unzen lava dome, may be particularly susceptible and unstable under loading events. Load oscillations cause strain rate to increase in the samples, and in the case of samples that failed, this increasing strain rate accelerated prior to failure. As such, monitoring changes in creep rate, in particular in response to any external forcing events, may be critical for understanding long-term stability, a point as relevant to other natural and engineered structures in seismically active areas as it is to Mount Unzen. I'd like to thank you all for listening once again, and thank the conveners once more for the invitation, and ask you to please contact me if you have any questions.